Welcome back to another edition of an AP stat lesson. And we are continuing into chapter 1, where we are continuing to explore data. Last class and last lesson, we looked at categorical variables and how to organize them in graphs and charts. We talked about the difference between frequency and relative frequency. And we discussed what not to do when creating a graph, like being aware of the scaling on our axes and how we should not use pictures as a pictograph. Today, we're going to move into the other type of variable, which is a quantitative variable, a numerical variable. We're going to find ways to properly describe a distribution of a quantitative variable, and then we're going to learn how to make distributions on our calculator. So if you do not have one with you, right now you should pause the video and grab your TI-84 and put it right next to you because you will need it today. There are a couple of ways to organize quantitative variables. The easiest way to organize a quantitative variable is called a dot plot. Okay, each data value is shown as a dot above its location on a line. For example, they'll see below is the number of goals scored. And I believe this is for the U.S. Women's Olympic team or World Cup team quite a few years back. So each dot represents the number of goals scored in a single game. And you will see most of them are around 1 to 4 goals. And there are a couple of high scoring games where you had a 13 and a 14. So how do we make a dot plot? Well, we want to draw a horizontal axis and label it with a variable name. So in our case, we drew a horizontal axis and we called it number of goals scored. We want to scale the axis from the minimum to the maximum value, and just like we did with our categorical variables, make sure your scaling is accurate and consistent. And mark a dot above the location on the horizontal axis corresponding to each data value. So in our case, each data point represents a game. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25 total games. And then each dot will represent how many goals were scored in that game. Okay. And this is, yes, the 2012 U.S. women's soccer team. Okay, so you'll see the data points here. This is the actual data, and this is a distribution of that data. It's a pictorial distribution of the data you see. Okay, because remember, our first step when we're analyzing data is to put it into some sort of graph or distribution. So dot plot is the easiest way to show a quantitative distribution. When we are examining a distribution, we want to be able to describe it, right? We look at a distribution and we want to say, okay, what do I see? And we want to be consistent in the way that we describe distributions. So when you describe or examine a distribution of a quantitative variable, you want to look at the overall pattern and look for anything that deviates from the overall pattern. Okay? To describe the overall pattern of a distribution, you're going to use the acronym CUS. It's the center, any unusual features, the shape, and the spread. Okay? When I talk about unusual features, I'm talking about outliers. Outliers are any values that deviate from the overall pattern of the distribution. So where is the center of the distribution approximately? What is the approximate shape of the distribution? What is the spread? And are there any unusual features or outliers of a distribution? So every time we talk about describing a quantitative distribution, these are the aspects we're looking for. Now in your textbook, I believe they call it SOX, but I like to call it CUS. SOX, I believe, is shape, outlier, center, spread. I call it CUS, center, unusual feature, shape, spread. Same thing. Okay? So this is how we describe, in words, a distribution. When we're describing shape, we're looking for really one of two things. Is it roughly symmetric or is it roughly skewed? Okay. When I'm talking about symmetric versus skewness, symmetric means that there is roughly the same number of observations on the right and the left side of the center. Okay. If something is skewed right or skewed left, it means that there are more values on one side or the other. Okay. For example, this data here is roughly symmetric. Okay, this data in the middle is skewed to the left because there are more values to the right, so the skewness is where there are less values. Okay, so this is skewed to the left, and skewed to the right means that there are more values to the left and less values to the right. So this is skewed right, the middle is skewed left, and the left graph is roughly symmetric. Now you'll notice that every time I use the word symmetric, I put the word roughly or approximately in front of it. That is because it is nearly impossible for a distribution to be exactly symmetric. So when we were describing distributions, and when we were describing a lot of things in stat class, nothing is ever perfect. So we use these fluffy words like roughly and approximately in front of them to give us some wiggle room for error. Okay, so this distribution is roughly symmetric. If you don't use the word roughly or approximately, that means you're implying that it is perfectly symmetric, and that will be marked wrong. Okay, so that is describing the shape. So again, we have center, unusual features, shape, and spread. Shape is roughly symmetric, skewed right or skewed left. When we're comparing distributions, we want to compare using our acronym CUS or SOX. So when we're comparing two distributions here, I'm looking at the South Africa versus the UK and the number of people that are in a household. Okay, so looking at these two distributions, I can describe them and compare them. So let's first compare their centers. I'm looking at the South Africa center. It looks like it's around 7, 6 or 7, but definitely skewed to the right. So the center would be about 6 or 7 people, whereas in UK it's probably between 4 and 5 people. So the center is definitely larger in South Africa than it is in the UK. Unusual features, meaning outliers. This point right here, this 26 or 27, that's definitely an outlier. That's a lot of people in one house. Even this 15 may be an outlier. So when I'm talking about outliers, I'm just pointing to points and saying these things might be outliers. Later in this chapter, we will mathematically calculate outliers, but right now we're just looking at the overall picture and what points could be an outlier. So these two look like outliers. In the UK, it doesn't look like I have any outliers in that distribution. The shape, South Africa is definitely skewed right. Okay, there's a lot of values right here, and it's skewed to the right with these outliers over here. Outliers are going to create skewness in that direction. So if you have outliers that are very large, like I do here in South Africa, it's going to create skewness in the right direction. Whereas the UK doesn't seem to have any skewness. In fact, I would say it's roughly symmetric. Not perfectly symmetric, just roughly symmetric. And then the spread. We haven't talked much about spread and how to describe the spread, but just looking at these two distributions, I would say that South Africa has a larger spread because they have more values spread out between 3 and 27, whereas the UK is really between 3 and 6. So therefore, the South African distribution spread is definitely larger. Okay. That we could talk about reasons why that this is happening, but that's where data analysis starts. We look at these distributions, we analyze them, and then we say, okay, why might this be occurring? And then we can move on into bigger questions like inference testing, and that's the overall outline of data analysis. Another type of distribution that we can use besides dot plots is a stem plot, also known as a stem and leaf plot. Okay, stem plots give us a quick picture of a distribution while including the actual numerical values. Okay, so how can we make a stem plot? Well, you're going to separate each observation into a stem, which is all but the final digit, and then a leaf, which is the final digit. Okay, we're going to write all possible stems from smallest to largest in a vertical column, and draw a vertical line to the right of the column. Then we're going to write each leaf in the row to the right of its stem. We're going to arrange the leaves from smallest to biggest, and then we're going to provide a key that explains in context what the stems and the leaves represent. You've all created stem and leaf plots probably back in middle school, so let's look at an example. Here is data that represents responses from 20 female AP Stat students. That said, the question was, how many pairs of shoes do you have? And these are the answers we got from 20 female AP Stat students. Yes, 51 is a lot of shoes. But I want to take this and put it into a stem and leaf plot. So I'm going to make my stems 1 through 5. That's because my smallest number is 13, a 1 is in the 10 spot, and my largest number is 57, and a 5 is in the 10 spots. Therefore, these are all my 10s. Then I want to create my leaves. So this is red, this 1, 9 is read as 19, is that value right there. 1, 3 is read as 13, and you'll notice that there's 3 3s because there are 3 13s, one here, and one here. Okay, so this is the 10 spot, and these are all my 1s. Once I add the leaves, I want to put them in order. So my smallest number is 13, and my biggest number is 5, 7, 57, and everything in between. Then of course I want to have a key. My key would say, okay, 4, 9 represents a female student who reported to have 49 pairs of shoes. You see how this is in context? It's important that we put all of our keys in context of the problem. And this is a stem and leaf plot. It's a great way to organize data and still have the numerical values. So if you look at this, you can almost turn this stem and leaf plot sideways, and it would be almost a dot plot, where you can kind of get an overall picture of the distribution. Okay. When data values are bunched up, we can get a better picture by splitting the stems. You could also, if we wanted to compare two types of quantitative variables, we can do a back-to-back stem plot. So I'll show you both of those. So here are the data for the females. This is the data. And then I asked the same question to the males. And here is the data for the males. Okay, so I'm going to split the stems like so. So now numbers 0 through 5 would be in the first row, whereas numbers 6 through 9 would be here, and so forth for every single stem and leaf. So my leaves 0 through 5, my leaves 6 through 9, my leaves 0 through 5, or 0 through 4, sorry, and then 5 through 9, and then 0 through 4, and then 5 through 9. Okay, so now when I split my stems, here's my males on the right side. So this means this is 4, this is 5, this number is 10, this 1, 4 is 14. Okay, this is 35, 38. Now, since I want to compare the males and females, I'm going to put them in a back-to-back stem plot. So the right side is males, and I'll draw another line, and my left side is females. And now I can compare the males and females because I have back-to-back stem and leaf plots, and I can look at the overall distributions. Looking at this stem and leaf plot, I can see that a lot of males are between 4 and 14 pairs of shoes. Right? There's a lot bunched up there. It looks like the males distribution is kind of skewed to the right, and you can see that the females are definitely overall owning more shoes than the males. And then we can kind of compare those two distributions on a back-to-back stem and leaf plot. And again, my key, which is in context of the problem. So we split our stems. We created a back-to-back stem and leaf plot to compare distributions. Another way to organize quantitative variables in a distribution is called a histogram. And this is the most common way that you will be, most common distribution of a quantitative variable. So you'll be looking at a lot of histograms throughout the year, and you'll be creating a lot of histograms. So what's a histogram? Well, how do we make one? We're going to divide the range of data into classes of equal width. We're going to find the count frequency, or the percent, which is relative frequency. So we can make a frequency histogram or a relative frequency histogram. And then we're going to label and scale our axes. A histogram is going to look like kind of a bar graph, but it's not a bar graph. Bar graphs are for categorical variables. Histograms are for quantitative variables. So it's going to look like a bar graph, but it's not a bar graph. So let's look. So here is a frequency table. And this table represents the percent of residents from each state who were born outside of the U.S. So it's a frequency table. So that means that here it says 0 to 5. That means 20 states had 0 to 5% of their residents born outside of the U.S. 13 states had 5 to 10% of their residents born outside of the U.S. 9 states had 10 to 15% of their residents born outside of the U.S., and so forth until we have one state that has 25 to 30% of their residents born outside of the U.S. Now we can try to figure out what state that may be. My guess would be probably New York, due to New York City being there. But I don't have the answer to that question. So this is a frequency table. Now just so you know, this is not data. This is a table that organizes data. If we had actual data, I would be looking at the 50 individual data points, right? So I would have all 50 states listed out and the percentage of residents that were born outside of the U.S. That would be data. This is a table that organizes my data. It's a frequency table. Okay, so this is not data. This is an organization of data. A frequency histogram looks like this. So my x-axis is the percent of foreign-born residents, and then my y-axis is frequency, which is the number of states. So between 0 and 5%, I have 20 states. And that's why my bar goes to 20. Between 5 and 10%, I have 13 states. And that's why I have my bar up to 13. Notice that my bars are touching. Okay? In a bar graph, they don't touch because they're different categories, but in a histogram, they usually touch. Okay? Looking at this histogram, I can describe it using CUS. And to me, this is a skewed right distribution. The center is probably between around 10% is probably the center. Yeah, so there's the center and the shape. Okay, I don't know if there's any outliers, unusual features, and the spread. Again, we haven't talked much about spread. We will talk more about it moving forward and how to put a numerical value to spread. So this is a frequency histogram. Sometimes it's better to make a relative frequency histogram. So on the left is the table we just looked at. On the right is the relative frequency. So instead of counts, we're looking at percents. So 40% of the states have 0 to 5% of their residents born outside the U.S. And the histogram that you see below it is a relative frequency histogram. And that is because the y-axis is in percents. Whereas in the first one we looked at, the y-axis was in counts. A relative frequency histogram is often used because then you can analyze two different variables that have two different number of observations. Okay, so relative frequency is usually used more often than just frequency. Okay. So, using histograms wisely. Here are several cautions based on common mistakes students make when using histograms. Number one, don't confuse a histogram and bar graph. Like I said, bar graphs are for categorical variables. Histograms are for quantitative variables. The x-axis of a bar graph is categories. The x-axis of a histogram is numerical values. Don't use counts or percents as data. Like I said, the data is the individual data points. If you have a table, like a frequency table or a relative frequency table, that means that you already have an organization of your data. That's not actual data. Okay, use percent instead of counts when you are looking at different distributions with different number of observations, like I said. And lastly, the most important one is just because a graph looks nice doesn't mean it's actually meaningful. So organizing data is very important. Putting it into a type of distribution is super important, but that does not tell us the whole picture of what's happening in our data. So we'll learn more ways of how to analyze data, but right now, all we know is how to organize it into a graph or a picture or a distribution. And just got to be aware that they don't always tell the full story. So what we're going to do now is we're going to create a histogram on our calculator. And we're going to use the data of the 20 female AP Stat students, and we ask them how many pairs of shoes they have. So I'm going to exit on my PowerPoint, and you should all have your TI-84, and I'm going to pull my TI-84 up right here. And this is kind of what you see, right? You have an open screen. When we are inputting data, we are going to hit Stat, which is right here, Stat. And then the first option is Edit, so we hit Enter. And now we can input data into any list we want. So I already have the data input into list 1. So I'm going to go back to the PowerPoint so you can see the data. At this point, you should pause the video so you can look at the data and input it into list 1. Now that my data is in list 1, I want to get out of lists. In order to get out of it, I have to quit. Quit is the blue button above mode. So I hit seconds and then mode, and it quits. And it puts me back onto a blank screen. Now, all of our stat plots and all of our distributions that we make this year are going to be in a category called stat plot. And it is the blue button above y equals. So we're going to hit seconds and then hit y equals, and you'll have the options for various stat plots. Plot number 1 is probably off for you. So you want to go into plot number 1. So you hit enter. And we want to turn stat plot 1 on. So to do that, you can toggle back and forth. So you want to be on and hit enter. When you hit enter, it will flash on. Now, if you go down to types of graphs, the one that we want to do is a histogram. If you look at all of the pictures, there's one picture that looks like a bar graph or a histogram, and that is the one that we want. So you want to highlight it and hit enter. When you do that, you're going to have the opportunity to change what's called your X list. Your X list is your X axis. It wants to know where is your data. You all probably put your data into list 1. So therefore, this should say list 1. If you didn't put it into list 1, let's say you put it into L2, then this should say L2 or L3. So wherever you put your data, that's what this should say. It's asking where is your list. Your frequency should be 1. Okay? And then you hit graph. And when you hit graph, you're probably going to see nothing. Okay? For some of you, you are going to see a line. That is because in your y equals, you probably have a function. You should get rid of that function. Okay? You hit graph. Okay? We still don't see anything. That's because our window is all messed up. A TI-84 has this great function where you can change the window without trying to mess around with it. If you hit zoom, you'll have all these zoom options. Because we are in stat plot, we're going to go down to number 9, which says zoom stat. And it's going to fit your window to the data that you have for your stat plot. So when you hit zoom stat, boom, you see a histogram. Okay? Mr. How do we analyze the histogram? How do we know the numerical values? And if you hit trace, you can now scroll back and forth on top of each of the bars of the histogram. So my first bar, you can see the minimum and the maximum of the bar. So this represents the width of 5 to 15.4. This n equals 5 means that there are 5 observations in this numerical value. So again, we're talking about the number of shoes that students own. So that means that 5 students own between 5 and 15.4 shoes. If I scroll over, you'll see that I have 5 students that own 15.4 to 25.8 shoes. I can scroll over some more and go down here. It says 1 student owns 36.2 to 46.6 shoes. Now you might be thinking, wow, this is weird. Why do I have so many decimals when I talk about the number of shoes? Well, your calculator calculated these widths for you, but you can certainly change the width once you're here. Okay, so if I wanted to change the width of each of these bars, I can go into my window and I can look at my X min and X max. So let's just say my min was 5, and let's go down to my max, which I'll make 70. Okay. And let's just say that my X scale, actually let's go to 75. And my X scale, which currently is 10.4, let's make it, I don't know, 10. Okay, now this is the width of each of my X values. Okay, so when I hit graph, it looks a little different. Now you'll see that this one bar here is out of my window, so I'm going to increase the Y values. So the Y max is currently 5.85. I'm going to make it 8. And then when I hit graph again, this is a little bit different version of the histogram we looked at. If we hit trace, you'll now see that my width of each bar is now 10, whereas before it was a weird decimal. And now, if I was to continue to scroll over, you would see the number of observations in each width. So by hitting zoom stat, we were able to get a general idea of the histogram. But if we wanted a more specific histogram, we can go in and just change the window so that the scaling is exactly the way that we want it. Okay? If I was to draw this on my paper, I would need to make sure I label my x-axis, label my y-axis, and give my histogram a title. Make sure my histogram has a title. So an x-axis, a y-axis, and a title. And that is how you make a histogram on your calculator. You input data into stat. You use your stat plots to turn a stat plot on, and then this is your histogram picture to make a nice looking histogram. Okay, I hope you learned something, and I'll see you guys in the next lesson of AP Stat, Chapter 1.3.